The manufacturing process starts by cutting double-sided copper-clad laminates to the size of the panels. A double-sided CCL is like the single-sided laminate, but with two sheets of copper laminated to the core. The customer and manufacturer agree on the desired type of core material, according to the principles mentioned before for single-sided PCBs. However, a CCL with a lower copper sheet thickness than the desired one is always selected to begin with. The additional copper is grown on top of the CCL during the plating process. Some manufacturers laminate the copper foils to the core themselves. Most prefer pre-laminated double-sided CCLs as the base material. The cutting process is exactly the same with the one described before for single-sided PCBs. In this stage, only the holes to be plated are drilled. This is a good time to introduce the type of holes found in double-sided PCBs. These are plated through holes and non-plated holes. Plated holes have a layer of copper deposited on the inside wall of the hole, supported by a copper annular ring on both sides. When used to create a conductive path between top and bottom copper layers, it is called a via. In double-sided PCBs, most component lead mounting holes are plated, even if there is no reason to electrically connect the two layers. This is done to improve conductivity and solderability during the assembly process. Pads of plated holes do not peel off as easily as the ones of non-plated holes. Non-plated holes are usually used for mechanical support and are drilled much later. Sometimes, if the design allows it, manufacturers prefer to drill and plate all holes in once, to save the extra drilling step. The drilling process is the same as the one described before for single-sided PCBs. This is the process where a layer of copper is deposited on both copper conductive sheets and the exposed core material at the walls of drilled holes. The process is necessary to create the plated through holes and increase copper track thickness to the desired value. There are two plating methods used by the industry: panel and pattern plating. In panel plating, the entire surface area and holes are plated at the same amount simultaneously. The conductive pattern is formed later by etching away the unwanted copper. This is a subtractive process where most of the deposited copper is removed later. Panel plating is a simpler process, requiring fewer steps and thus lower production cost. However, precise features and thin lines are more difficult to form, due to the thick layer of copper that must be etched away. In pattern plating, only the desired circuit pattern and holes are plated. It is a complicated process that requires a plating resist to be applied and imaged before the process starts. Then, copper is deposited only on the exposed pattern. The excess copper is later etched away. This is a semi-additive process where less copper is consumed and later removed. Less copper to be etched allows for more precise and fine patterns. However, the production cost is higher and requires a tin or etch resist coating to be applied on the grown pattern before the etching process. Both methods are widely used for double-sided boards, while the choice of plating method defines the etching process. To make things simpler, this section will focus on the panel plating method, while pattern plating is explained in the multilayer PCB videos. The process is done in the plating area. The machines and tools used are drilled and deburred panels, electroless copper plating line, electroplating copper plating line, lots of chemicals and water. Copper buildup is done in two steps. The first is to use the slow electroless plating method to deposit a thin layer of copper on the surface and the walls of drilled holes. Then, when all surfaces are made conductive, the much faster electrolytic plating, or electroplating, immediately follows to reach the desired copper thickness value. Their major difference is that electroplating needs electricity, while electroless does not. Electroless plating is an autocatalytic immersion plating process. For the autocatalytic chemical reaction to take place, we need an aqueous solution of positive copper ions, a chemical reducing agent and a catalytic surface. In the plating bath, the copper ions are provided by copper salts like copper sulfate. The reducing agent, usually formaldehyde, donates electrons to the copper ions, reducing them to metal atoms that are deposited on all catalytic surfaces. For PCBs, the copper sheets are catalytic in nature, but the dielectric core is not. Thus, the activation or catalyst treatment step is needed to coat the surface with a thin film of a catalytic precious metal, like palladium. Now, let's have a look at the electroless plating line. Before all begin, the surface to be plated must be perfectly clean. The usual cleaning process of chemical clean, water rinse, micro-etch, water rinse, acid rinse and final water rinse is done to prepare the panels for the activation step. In the palladium stannous chloride catalyst system, the activation bath consists of palladium chloride and stannous chloride in hydrochloric acid solution. The stannous ions are absorbed by the surface of the dielectric material and reduce the palladium ions to atoms, forming the film on the surface. Sometimes the panels are first immersed to a sensitizing or pre-activation bath of stannous chloride in hydrochloric acid solution to improve ion absorption. The activation chemical treatment process creates byproducts that will slow down and compromise the plating process. Therefore, the panels are immersed in an alkaline bath to clean them. Now that all surfaces are made catalytic, the panels are immersed on the plating bath. Electroless plating creates a uniform layer of copper on all surfaces, no matter the geometry, but is a slow process. On average, the deposition rate is 1 micrometer per hour. Many things can and go wrong here. The temperature, pH, reducing agent and copper ion concentrations in the bath need constant monitoring and adjustment. Because it is a very slow and expensive process, it is only used to create a thin copper layer of 1 to 2 micrometers. When the desired thickness is achieved, the panels go through the final acid and water rinse. Now that all surfaces are made conductive, the panels are electroplated until the desired copper thickness value is reached. Electroplating is an electrochemical process by which copper is deposited on all conductive surfaces. The process needs a power source, 2 electrodes called anode and cathode, and an electrolyte to form an electrolytic cell. The electrolyte is a conductive solution containing a soluble copper salt. The conductive surface to be plated, here the panels, is connected to the cathode. The metal to be deposited, in this case copper, is connected to the anode. When both electrodes are fully immersed in the electrolytic solution, the power is switched on. The power supply supplies a direct current to the anode that oxidizes the metallic copper to copper ions. These positively charged ions, along with copper ions supplied by the electrolytic bath, are attracted to the cathode. There, they gain 2 electrons and are reduced to metallic copper. In practice, the electroplating process starts with the necessary chemical cleaning of the electroless plated panels. Because copper oxidizes fast, to save the extra cleaning steps, electroplating must follow immediately after electroless plating. In this process, deposition rate is proportional to the electric current passing through the solution, but also depends on temperature, metal ion concentration, solution flow, pH, and quality of water. Copper deposition is achieved gradually by passing the panels through several closely monitored baths. On average, the deposition rate is about 1 micrometer per minute. At the end of the line, the panels are thoroughly washed and dried. This is the process where the conductive tracks of the electronic circuit are created by a chemical subtractive process called etching. For double-sided panel-plated boards, it requires the following steps. Photoresist film application on both sides of the board. Photomasks alignment and UV exposure of both sides. Photoresist development. Unhardened photoresist removal. Copper etching. Cured photoresist removal. The process is done in the exposure and etching areas. The machines and tools used in this process are the drilled panel plated panels, a chemical clean line, dry photoresist film laminator, UV exposure machine and photo masks, a develop etch strip line, chemicals for resist stripping and copper etching. The process is mostly the same with the one mentioned for single-sided PCBs. The only difference is that both sides of the board go through the photoresist lamination and UV exposure process. How this is done depends on the manufacturer. Many use double-sided film laminators and UV exposure machines, while others do one side first and then manually turn over the board and do the second. In this process, the alignment of top and bottom side photomasks during UV exposure is crucial. Some UV exposure machines have pins on the corners of the exposure plate, where the photomasks are secured using the registration holes punched during the plotting stage. The more advanced UV machines do this automatically through an optical alignment system. After the exposure stage, the rest of the process is the same with the one mentioned for single-sided PCBs. This is the process where the etched panels are optically inspected for defects in copper patterns. The process is done in the quality inspection area. The machines and tools used are etch panels, Gerber files, automatic optical inspection machine. The process is the same as the one explained for single-sided PCBs. The operator usually checks one side first, turns around the board and then checks the other. Automatic inspection machines cannot check the thickness and quality of plated holes. The only way to check that is to cut a cross-section of a random board and measure the thickness of plated walls. However, manufacturers do not want to waste a full board, so they are using test coupons instead. Test coupons are placed in the empty area, usually on the borders and middle of the panel. They must contain holes and tracks with dimensions reflecting the actual PCB board characteristics. Coupon style, number per panel and location follow IPC's 2221 standard recommendations depending on PCB type and class. The design and placement of the coupons is done by the manufacturer during the panelization process. If the empty area on a panel is not enough, the panel is rearranged with less boards to make space for the coupons. For double-sided Class 1 PCBs, the test coupon used for plated hole evaluation consists of a grid of the same plated holes used in the PCB. Two such coupons are placed in opposite corners of each panel. If the plating process works correctly for the holes and copper patterns in the test coupon, it is assumed that all holes of the panel are plated successfully. Inspecting plating holes is done using the microsectioning or else cross-section analysis process. The process is done in the quality inspection area. The machines and tools used are test coupon, precision diamond saw to cut a thin cross-section out of the coupon, grinding and polishing tools, microscope with specific software. Micro-sectioning is a sample destructive process. It starts with cutting a thin cross-section piece out of the coupon using a diamond saw to create a test specimen. The specimen is embedded in resin for easy handling. Then, the surface is grinded and polished to create a very smooth light reflective surface that can be placed under the microscope. The image of the cross-section, showing the plated walls, is inspected and copper-plated thickness is measured using the specific software. If everything is okay, the panels are ready for solder mask application. If not, the production line stops and the plating process is readjusted. Please watch our final steps of production video for the solder mask application, surface finish and silk screen steps.